All right, welcome back. Hopefully we're rolling through this stuff. We're on section 2.5. This is the last section of the second unit. Okay, we should be getting a little bit close to midterms right about now. And really with our math content, we're about halfway through the year, or through the term, sorry. But anyways, today we're going to be talking about functions as rules and tables. And the target's a little bit different today. And it just says that I can use a table to describe a function. Well, we better know what some things are here. We're going to be dealing with these two sets called domain and range. Maybe you've heard of them before, maybe you haven't. So the domain is the set containing all the input values. Okay, which we can usually think of as the x values. Okay, most of the time we do have x and y values, so these are the numbers that you're putting into the function. The range would be the set containing, wow, I gotta spell right. Try that again. Containing, forgot an N, all output values. And those we know as the y values. Okay, we have an x and a y. We throw one number in, we get another number out. So what these things build when we have input and output values, we're really talking about a function. Now a function is a pairing such that each input is paired with exactly one output. So for every number that we put in, we only get one number out. So things like, it wouldn't be a function if I could put a 3 into the function and get two different numbers. That would not be a function. Let's just put it that way. So what I want to look at is the way I always see a function is it's this machine. It's kind of a goofy looking machine. All right, it's this old school kind of crank machine here. We have f of x. That's what we usually use to define a function of x. Now it has this little pipe here, and we put numbers like x's in there. Those are our inputs, and they go into the function. And what we get is it's got this big old blowhorn on the other end, and it's got this crank. Okay, and it's got this little crank handle here, and the handle comes up here, and we can turn that crank around and around and around, and when we put that number in, it spits out another number. Okay, and that's considered our output or our y. So we'll look at the idea of function here in a little bit, but for the most part, it's kind of like if you remember evaluating functions, which you've done already, and it asks you to evaluate the expression for different x values and find what it would equal. Well, you were actually finding these y values, and that's what we're going to be working with a lot today. But we also have to understand this idea of domain, range, and what a function is, and whether something is or is not a function. So this is a function because it spits out just one y. Okay, if it were to spit out, let's say this is y1, and it were to spit out a y2, since it has two y values, that would not be a function. So for the most part, what I'm looking for is I'm looking that every x has only one y. Okay, and whatever x may be, or whatever input only has one output. let's look down here at this table. This is based on the gas prices right now, which, you know, it's July, it's summertime, prices are a little high. And if I have 1 gallon of gas, that costs me $2.99 and then 9 tenths that they always do just to cheat you. It's basically $3. Okay, for 1 gallon of gas, it's 2.999. For 2 gallons of gas, it's 5.998. For 5 gallons of gas, it's 14.995. For 10 gallons of gas, it's 29.99. Okay, for 20 gallons, it's 59.98. Okay, and that's the price that it's going to cost you to get that many gallons. Okay, now it kind of makes sense that if you go to one gas station and you get 1 gallon of gas, or you get 1.5 gallons of gas, or whatever it is, that it's not going to, there's no way that it'll cost you different amounts of money, right? It's only going to be that $3. They're either going to, and for the most part, or for always, they round up, so they would pretty much charge you $3 for that 1 gallon, even if you just went and asked, hey, can I have 1 gallon of gas? They're going to charge you $3. Don't go there with $2.99 in exact change. They're going to round that bad boy up. But the main thing you need to focus on is that no matter how many gallons of gas, I cannot get two different prices. That just won't happen. Okay, I'm not going to get 5 gallons and it costs me 14.995, and I'm not going to get 5 gallons of gas and it costs me $20. Not at the same gas station. So this is a function. Let's talk about what the domain is. Whenever we show domain, we show it in this set. Okay, and the way you build a set, you have these curly braces. In fact, I'm pretty bad at drawing them, but just do your best. If you need an example, they're like the keys on a keyboard right above the enter. They're on the bottom. It's the square brackets, and up above them are these curly brackets or curly braces. I'm going to call them a million different things, I'm sure, but the domain is the set of all the input values, 1, 2, 5, 10, 20. For what we did in this function, we put in 1, 2, 5, 10, and 20. Okay? And we close that off in those curly braces. It'll get really lazy, or I'll get really lazy doing those later, and it'll just look like a couple squiggly lines. So just do your best to make it look good. The range, the prices I can get, are the 2.999, the 5.998, the 14.995, the 29.99, and the 59.98. Okay? Those are all the possible output values of this function that we did. We only described the function over these domain values, but when we plug in these domains, we get these ranges. Okay? So don't think of range as the statistics range where you're taking the highest one minus the lowest one. We don't do that here. Okay? Range is just defined as all the y values of whatever function you have. Okay? Let's talk about whether something is or is not a function. Now, what I have down here are a bunch of examples of teachers and what their first period class is. All right? Let's look at this as what really could be the case right now. I'm over here first period teaching Peak Math 1. Mr. Horning is teaching Algebra 2 maybe. I think Mrs. Healy might be doing pre-calculus. And Mr. Johnson is doing algebra principles. Okay? What I'm looking at here is everyone in the inputs. There's the inputs, there's the outputs. Every one of the inputs only goes to one output. So, like, I don't, and it makes sense to think of it this way because I can't teach multiple classes at once. Okay? I can't teach Peak Math 1 and Algebra Principles. I can't do that. So no teacher can. We have to make sure that no teacher can do that, or that no teacher is doing that. I'm going to one of them. Horning's going to one of them. Johnson goes to one. Healy goes to one. That's a function. So it's a lot of fun. Okay? It's a function. I'm going to abbreviate that. It's kind of fun. All right. Let's look at the next one. Maybe for this one, I am going to teach Peak Math 1 because I don't really like to leave our little wonderfulness here. Maybe Mr. Horning is teaching algebra principles, and maybe Mr. Johnson's teaching algebra principles too. And then Mrs. Healy decides to take on a little bit of algebra 2 and pre-calculus. Well, she can't do that. She's only one teacher, okay? And for one teacher to teach 2 different classes in the same period is just ridiculous, okay? Unless you're doing, kind of those advanced classes, maybe she was teaching a pre-calculus and she had 5 calculus kids in there and they were doing something smart and she was teaching the pre-calculus kids. I don't know. But for our case, this is not a function. This is no fun. No fun for Mrs. Healy trying to teach 2 classes at once. Okay? So that's a big key there, is that one input goes to 2 different outputs. That means it's not a function. No fun. All right, why don't you try this one? Let me draw it, and then I want you to pause the video and figure it out. Pause the video. Tell me whether or not that's a function. Okay, welcome back. So we've talked about functions being that one teacher can only teach one class in one period. Okay, so is this mapping a function? Well, let's look at it. I'm teaching algebra principles. Horning is teaching algebra principles. Healy is teaching algebra principles. And Johnson is teaching algebra principles. You think that's okay? Well, yeah, it is, because nobody's teaching more than one class. Even though a bunch of people are teaching algebra principles, that's fine. There's no issue with that. That's a lot of fun. A lot of teachers working together to teach the same subject. Okay, that is a function. Go ahead and turn the page, and we'll look at, we're going to look at trying these with numbers now. So I'm just going to throw some numbers in here. Let's look at the input being 4, 7, and 10. What you're going to do is you're going to tell whether or not these are a function, and then you're also going to state the domain and range. Let's use 0, 1, 2, and 3. Let's say 4 goes to 0, 7 goes to 1, and 10 goes to 3. All right. Notice there's this 2 in the output range, or sorry, not in the output range, but in the output set. But nothing hits it, okay? Nothing hits that poor little 2. That's fine, okay? Now 2 is the loneliest number, not 1. 1's being used, okay? Look that song up. It's pretty good. Hold on. Let's start off. Is this a function? Only one arrow coming from each number, so that's a lot of fun, okay? That's a function. Domain, all the numbers in the inputs, 4, 7, 10. The range, all the numbers that got hit in the outputs. Well, the numbers that got hit were 0, 1, and 3. So we just put down 0, 1, 3. We don't need to worry so much about 2 because it wasn't hit. It wasn't involved. Okay, let's try another one. 1, 3, 5, and 7. And let's go with the evens over there. 2, 4, 6, and 8. All right. Let's look here. Let's say 1 goes to 2. They go to 2. They go to 2. And 6. And there. All right. So I have 1, 3, and 5 all going to 2. 5 and 7 going to 6. Okay. Well, if you notice there, I had 5 with 2 branches off of it. That's not okay. That 5 is not going to have fun. So no fun. Okay. I don't know why I put a decimal or a period after the no, but don't worry about that. Okay. Even though it's not a function, we still have to worry about domain and range. Wow, that was bad. Okay. Still have to worry about domain and range. All the numbers that have branches coming out of them, 1, 3, 5, and 7. 1, 3, 5, and 7. And the numbers that get hit in the range, 4 doesn't and 8 doesn't. They might as well not even be there. But 2 and 6 do. So 2, 6. See, I told you those brackets would get ugly at the end. All right, let's go ahead and I'm going to draw one up here, and you're going to pause the video and see what you think. Let's go 7, 8, 9, -4, -3, -2. And let's take 7 and -3. Trying to make an arrow there. We'll go 8 to -4 and 9 to -4. Kind of hard to track, but 7 goes to -3, 8 and 9 both go to -4. Pause the video, fill out the problem. All right, welcome back. Hopefully you understood this is a function. It's a lot of fun. Okay. No one number over here has two branches coming out of it. The domain 7, 8, and 9 branches coming from all those numbers, and the range -2 might as well not even be there, but we have -4 and -3. Okay, so that's the domain and range, and that tells us whether or not it's a function, and it is. Now let's look at tables. Okay, tables are a lot like these mappings that I had up here. I kind of like these. They're a lot of fun, but they take up a lot of room. Okay, tables are okay though. All I'm looking for is I'm looking to see, is there one number up here in the input section, in the input row, that is repeated and has a different number down here. I have 5, 7, 9, 14, 33. Those are all different. Okay, so since they're all different, for what I know, this is a function. This is fun. And the domain 5, 7, 9, 14, 33. All right, and the range, the output value is 11, 15, 19, 29, 67. All right. As per usual, I guess, when you're talking about functions, it's always easier to understand what a function is and isn't by looking at ones that aren't. If I look here, I have 2 5s in the input row with two different numbers. It's very key that they're different, because if this said 5, -12, even though they're repeated, it would still be a function because that's just the same point. Okay, if you're looking at points. So this is no fun. And again, even though it's no fun, we still have to worry about domain and range. So 4, 5, I don't have to write 5 twice. 6, 7. So 4, 5, 6, 7. And the range, the output values, -10, -12, -13, 14, and 16. All negative. -13, -14, and -16. A lot of times, if you notice that your list of ranges is bigger than your list of domains, it's probably not a function. Okay, there's 5 numbers down here, 4 there. That's not a good sign. Okay. All right. Now we're going to move on, and we're going to write rules for functions. So we're given the table, and we're going to write a rule on how do I get from the input, or the x, to the output y. So what do I do here? To go from 4 to 8, there's a bunch of things I can do. I can add 4, I can multiply by 2. I could probably multiply by 4 and subtract 8. That would work. Okay, multiply 2 and subtract 4. One of those methods, I could even divide by stuff here. I could divide by 2 and add 6. 4 divided by 2 is 2, plus 6 is 8. So there's a lot of options that can work. But what you have to do is you have to test it all the way down the row and find one that fits for those numbers. Let's say I'm going to go with the easy one. I'm going to think, what if it's times 2? Okay, 4 times 2 is 8. Well, is 7 times 2 11? No, it's not. Okay, so times 2 didn't work. What about plus 4? 4 plus 4 is 8. What's 7 plus 4? Well, 7 plus 4 is 11. 10 plus 4 is 14. And plus 4 there. That ends up working. 13 plus 4 is 17. So what I want to do is I want to say to get y is equal to whatever number I start with plus 4. X plus 4. That's kind of nice, huh? That looks real good. I can check it real quick. Let's try 4. 4 plus 4, well, that's 8. 7 plus 4, 11. 10 plus 4, 14. 13 plus 4, 17. It's awesome. It works. It's sweet. All right, let's go to the next one. Again, how do I get from my x's to my y's? X to y. 5 to 7, I could probably add 2. Let's think about that. So going from 5 to 7, if I add 2, does 7 plus 2 equal 11? No, it doesn't. 7 plus 2 is 9, so it's not add 2. Next one I usually think about is like multiply. So if I multiplied 5 by 2, 5 times 2 is what? Yeah, 10. Okay. So 5 times 2 is 10. Minus what would give me 7? 10 minus 3 would give me 7. So let's look at times 2 and then add 3. Sorry, subtract 3. I even just said it. Subtract 3. So if I'm going to multiply this number by 2, 7 times 2 is 14. 14 minus 3, hey, that's 11. Let's try it again. 10 times 2 is 20, minus 3 is 17. And 14 times 2 is 28, minus 3 is 25. All right, I think I found it. Now I need to find a way to write it. So to get my y, I want to take x, multiply it by 2, and subtract 3. Okay? Just remember that we're always doing our multiplication before subtraction. All right? I want you to go ahead and pause the video and try the next 2. All right, welcome back. Those might have taken me a little bit of time. Now for this one, it looks like, sometimes I want to just look at the whole row and try to figure out a pattern. Okay, it looks like a half, right? 1/2 of 4 is 2. 1/2 of 8 is 4. 1/2 of 10 is 5. Okay, but these ones down here are negatives. What the heck am I going to do there? Well, I could multiply my x. I want to cut it in half. I want to multiply it by a half to get the number right. To get the sign right, well, a negative times a positive is always going to be a negative. So I can just multiply it by 1/2. And multiply it by a negative, I mean. So to get my y's, I'm going to multiply by negative 1/2 x. Okay. Now, let's look at the next one. One thing that I really like is anytime I'm given a 0 as an input. Okay? 0 as an input always means something. So remember, if you multiply or divide by 0, well, not divide by 0, but if you divide 0 by anything, or if you multiply 0 by anything, you're always going to get 0. So even if there is some sort of multiplication here, we're still going to have to add 1 in order to get to this 1. All right, does that kind of make sense? You can go ahead and try it. 5 times, times 0 is, and that's always going to be 0. And then you add 1, you're going to get that 1. 5,000 times 0 plus 1 is going to be 1. Anything times 0 plus 1 is going to equal 1. And that's the only way to get there. Okay, that's the only way that we have to get there. So now we have to figure out how to make these other things work and what number we're going to multiply or divide by the x. So to go from -1 to -2, well, I'm going to have to add that 1 on there. So I can kind of add that 1 here. Or no, what I want to do is I want to look at, let's say, come on. What number plus a, I'm just going to forget about that negative. I don't like it. I lost my train of thought. Okay, it happens to the best of us. I'm going to look at these two because they're positive. I really like working with positives anyways. All right, so I'm going to multiply by some number and then add 1 and see if I can get 4. Well, 3 times 1 would be 3, plus 1 would be 4. So I'm thinking I'm going to multiply by 3 and then add 1. What's 2 times 3? 6 plus 1 is 7. I'm thinking it's 3. All right. Let's double check it with our negative group. That kind of ticked me off here. So -1 times 3. -1 times 3 is -3. Plus 1 is -2. I think we have our answer. Since we're multiplying by 3 and adding 1, we're going to have 3x plus 1. That's how we get our y's. Okay? Kind of ugly, but it's a good problem. All right, now we're going to wrap this up with a pretty easy idea. We've done this before. We're just going to put it into place on somewhere that we're actually going to use it for quite a bit of our math careers. It's just filling in function tables, filling in input-output tables. Okay? And what you're going to do here is remember that great stuff that you learned when we were evaluating expressions? You're going to use that here. All right? We're going to take this input of 2 and put it in for x. We're going to put that 2 right into x. Okay? And just replace that with x and figure out what we have. 5 times 2 is 10, plus 2 is 12. Okay, this is where we really get to use our function machine. Remember that picture I drew? Okay, we have this function machine here, and it's going to spit out a number. Well, that function machine is 5x plus 2. That's what it does when you turn that crank. So you're going to put a 3 in. 3 times 5 is 15, plus 2 is 17. Okay? And you can picture doing that with all these numbers. 4 times 5 is 20, plus 2 is 22. 5 times 5 is 25, plus 2 is 27. Okay? Now, that's just that, it's that great stuff that we used in evaluating expressions. I think it was like 2 sections ago. And we're putting it to good use here. All right, let's go to the next one. If you want to pause it and try it, you can. Feel free, but I'm just going to go ahead and do it to keep our time down a little bit here. -8 times 4 is -32. Minus 2 is -34. -2 times 8, or sorry, -2 times 4 is -8. Minus 2 is -10. 0, I love multiplying by 0. 0 times 4 is 0. Minus 2, so usually when I multiply by 0, I just get that piece there. That's really cool. And 4 times 4 is 16. Minus 2 is 14. All right. I know a long day, but we're really talking about some new stuff here, and this is really cool math stuff. We're really getting into the algebra of the year. Okay. So I promise videos will be shorter. This one did get a little bit long, but you'll get a treat after this, like always. Okay. Go ahead and summarize your notes, finish the practice and the application, get all that stuff checked, and good luck on the Mastery Challenge. Keep it mathy out there. All right, we are on the last video of this section. So we have the top 5 football trick plays. Number 5 was the Oregon wide receiver reverse pass to the quarterback. Number 4, the wrong ball play. Number 3, the Statue of Liberty. Number 2, the fake Statue of Liberty. And we're going to round off our top 5 countdown with the Presbyterian bounce pass. I hope you enjoy, and good luck on the review and test for this unit. Good job. Bye.
Now, Presbyterian playing its first game ever against the BCS team Wake Forest. You can't spell Presbyterian without tricky. All right, well, you can, but you get the point. How about this play? They faked them out. They thought it was over, and then they bounce it. It's a back.
The old lateral, not dead. That's a great call right there.
Look, wow. You think, oh, it's on the turf. Everybody stops. No, heaves it down the field. The execution, the tosses, perfect. Excellent job by Presbyterian.